All right. So we'll be discussing about the gas power cycles. So we'll go over through with the Carnot cycle, Otto cycle, and then we will concentrate on the diesel cycle, which is applicable for marine engineers. So we will have an overview of the reciprocating engines. Um, we have these terms like the top dead center, bottom dead center, and then bore. Okay, so the difference or the travel rather, the travel of the piston from the bottom dead center up to the top dead center is called a stroke. Okay, so the length of the piston travels from bottom dead center to top dead center. And then the piston diameter is called bore. Okay, so it's called bore. So as I've said, the distance between the top dead center and bottom dead center is the largest distance that the piston can travel in one direction. And it is called stroke. Okay, stroke. And bore is the diameter of the piston. Or sometimes they say that it's the inside diameter of the cylinder. Okay, so the air or air fuel mixture is drawn through the intake valve and then expelled. So you have your combustion products. It will be expelled through the exhaust valve. Okay, exhaust valve. So clearance volume, the minimum volume formed in the cylinder when the piston is at the top dead center. So I forgot to mention that one. I'll show you in the next illustration. And then we have this displacement volume or volume displaced. So that is the volume wherein wherein the piston moves from the top dead center to bottom dead center, or from bottom dead center to top dead center. Okay, so we have this compression ratio, and in this compression ratio, you have your maximum volume divided by minimum volume. Okay, okay, so we now have the Carnot cycle, and this is the diagram. So we have the PV and TS diagram. So let me give you a sort of a code so that it will be easy to remember. Okay, so it will be easy to remember. So for the Carnot cycle, Carnot cycle, Carnot cycle. So what is our code? TS TS. I love ya. Okay, so TS TS. So what does it mean? Okay, so TS, this is isothermal heat addition. Okay, so isothermal or constant uh, temperature process. And then isentropic, isentropic uh, compression. And then, so isothermal heat rejection. So isothermal heat rejection. Let me write it here. And then isentropic expansion. Okay? So TS, TS. And for the PV diagram, so it's already in the book, but just Okay, so it's already in the presentation rather. So you have from 1 to 2. Okay, so 1 to 2 isothermal heat addition. Okay, so isothermal heat addition. Okay, so 1 to 2. So I might as well write it over here. So this is process 1 to 2, 2 to 3, 3 to 4, and then 4 to 1. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Thermal efficiency is 1 minus the low temperature divided by high temperature. And for the TS diagram, so uh, with constant S, okay, so you have a vertical line, constant S, isentropic, and then uh, constant T, okay, constant T, isothermal, okay, isothermal, horizontal line. So from the diagram, you can easily see where is Q in and Q out. So this is very important when you take your exam so that you won't be able to be confused. And with that, let's move on with the air standard assumptions. Okay. Um, for air standard assumptions, so the working fluid is air, and when we say cold air standard, then air will be at a temperature of 25 degrees C. And another thing is that R is 0.287 kilojoules per kilogram Kelvin. It's in the, I'll have that discussion later about the gas constant. Okay. So this, okay, so as I was explaining earlier, okay, so this area is the clearance volume, or sorry, the shaded area. Okay, so the shaded area over here, so that represents your clearance volume. And then this one, this shaded area over here is your displacement volume. Okay? That is the volume swept by the piston. Okay? So the volume swept by the piston is also called the displacement volume. Um, the stroke, as I've said, is the from top dead center to bottom dead center. Okay. Okay. So for the ideal cycle for your spark ignition engine, it is based from the Otto cycle. So spark ignition engines, also known as uh, gasoline engine. Okay, so for Otto cycle, okay, so for Otto cycle, okay, so for the Otto cycle, so Otto cycle, what is our code? SV SV. Okay, so SV SV. So isentropic compression. So isentropic compression. Then constant volume. So constant volume heat addition. Then isentropic expansion. And finally, constant volume. Constant volume heat rejection. Okay, so constant volume heat rejection. Okay, so Let me, so this is for process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, let's consider a, a spark ignition engine. So you have your piston cylinder assembly. So let's say that this is your piston. Okay, so this is the starting point. And then from there, okay, so from there, the valve opens, admitting air. Okay, so admitting air and fuel. So it's a mixture of air and fuel. So this is your intake stroke. So intake stroke. And then it undergoes compression. So it undergoes compression. Okay. So it undergoes compression. So the air and fuel mixture is now compressed. So it's now compressed. And upon compression, so you now have the process constant volume heat addition. Okay, so constant volume heat addition. So you now introduce the spark plug. So the spark plugs produces heat energy, and so the mixture of uh, air and fuel will be ignited through a spark plug. And with that, you now have your constant volume heat addition. So the piston will move down. The piston will move down. Okay, so the piston will now move down. The piston's over here because the gas is expanding. So the gas will now push the piston down. And so that is what you call power stroke. Power stroke. So I forgot compression stroke. Okay, so let me write it here. Compression stroke. Power stroke. And then we now have a constant volume heat rejection. Okay. So the valve will suddenly open. The exhaust valve will suddenly open. So what's the natural tendency of the flue gas? It will be released to its surrounding. So that is where constant volume heat rejection occurs. And the piston will continuously move up. Will continuously move up. Okay, so the piston will continuously move up. And so you now have your exhaust stroke. Exhaust stroke. Okay, so again, so you have your intake stroke, admitting air and fuel mixture, and then compression stroke. And you now have your constant volume heat addition. So with the spark ignition engine, we are using spark plugs. Okay, so that will ignite the air and fuel mixture. And with that, um, the gas will now push the piston down. And that is where we have the power stroke. Upon reaching the bottom dead center, the exhaust valve will open, and so the pressure is now released, and that is where constant volume heat rejection occurs. So the piston will continuously move up, and that is expelling all the exhaust gas, and that is now your exhaust stroke. Um, so going back with our code, S V S V. Okay, so S constant entropy. So S V. Okay, so from 2 to 3, constant volume. So this is P, then V. Okay, so we have a vertical line. So, and then 3 to 4, isentropic, constant entropy. And then 4 to 1. So again, S, V, S, V. Okay, so V, constant volume heat rejection. So from the diagram, you can easily identify which has the highest pressure and then lowest pressure. Heat energy is coming in and going out. We have these terms, four-stroke cycle and two-stroke cycle. Um, Surely you have heard of the two-stroke engine and four-stroke engine. So meaning in every cycle for a four-stroke engine or cycle is that you have four strokes and that leads with two revolution. So in two revolutions, one complete cycle, you produce one power stroke. Okay, so only one power stroke. You make two revolutions. Okay, so the the piston moves up and down, and then uh, in the crankcase, this one will move twice. This one will move twice. So as it moves twice, you have two complete revolution. You produce one power stroke. For a two-stroke engine or two-stroke cycle, you have one cycle and it only has two strokes, and that leads with one revolution. So for every revolution, it creates a power stroke. Okay? So two-stroke engine or two-stroke cycle, one complete revolution. Okay, so one complete revolution produces one power stroke. As opposed to four-stroke engine, you need two complete revolution. So four-stroke. So you have two complete revolution to produce one power stroke. Okay. So in that, as far as the difference between two-stroke engine and four-stroke engine, the two-stroke engine produces twice the power of the same size, okay? Same size, theoretically of the same size with the four-stroke engine. Um, so these are the working equations that you'll be using. Uh, but as I've said, we will concentrate on the diesel cycle. But the formula are almost the same. Okay, so this time we will concentrate on this topic, the ideal cycle for compression ignition engine, and that is the diesel cycle. So for a diesel cycle, uh, you have your MEP as work net over volume displacement. And volume displacement is the difference between the maximum and minimum volume. So we now have the diesel cycle, and we have this code again for the diesel cycle. So what's the code for the diesel cycle? SPSV. Okay, so diesel cycle. What's our code? SPSV. Okay, so SPSV. V. So same thing. This is isentropic compression. So same thing. Isentropic compression. So this is process 1 to 2. And then you have your constant pressure process. Constant pressure heat addition. So heat addition. And then so addition. Isentropic or constant entropy. So isentropic expansion. Okay, and then constant volume heat rejection. So this is process 1 to 2, isentropic compression, and then this is 2 to 3, and then this is 3 to 4, finally 4 to 1. Okay. So in the diesel cycle, so same thing. Let's consider this piston cylinder assembly. Okay, so this is your origin. Okay, this is your origin, and then the valve is inlet valve is open. So intake. So you now have air. Okay, so air. So intake stroke. Only air. Okay, so intake stroke. Air only. For the diesel, for the Otto cycle or Otto engine, for the gasoline engine, intake stroke is consists of air and fuel mixture. For the diesel, it's only air. Okay? So please take note of the difference. Otto, for the Otto cycle or the gasoline engine, okay, air and fuel mixture. For the diesel cycle or for the diesel engine, only air. Okay? So for the intake stroke, only air is allowed to get in the piston cylinder assembly. And then you now have your compression stroke. So you now have your compression stroke. Okay, so the valves are closed. Okay, so air is now compressed and it is now hot. Okay, so it's now hot, but it is so hot. It is so hot such that when the fuel injector uh, gives fuel, okay, so as it gives fuel, it will spray fuel. Okay, it will ignite. Okay, so it will ignite. It will ignite right away. So that is where your constant pressure heat addition occurs. So it goes like this. So you have your piston, and so as to maintain the pressure constant, the piston moves down until here. Okay, so until here. So while fuel is injected, okay, so you now have your uh, uh, constant pressure heat addition, and from there the piston continuously moves down, and so you have now completed your power stroke. Okay, so the flue gas is now expanded. Okay, okay. And then you now have your constant volume heat rejection. Okay, so constant volume heat rejection. So the valve suddenly opens. Of course, the pressure here is very high compared to the surrounding. So the tendency is that the flue gas or the combustible materials will exit the exhaust valve. And then the piston moves up, continually uh, going back to its original position. Okay, so that is the diesel cycle, or in this case, the diesel engine. Okay, so illustration of the diesel engine. So the another difference for the diesel engines and the gasoline engine is that instead of using a spark plug, to ignite the air and fuel mixture, you have your fuel injector, wherein air is only compressed during the compression stroke. So what's the code again for diesel? SPSV. Okay. Uh, okay, so again, S S P. Okay, so S P S V. S P S V. So from here in the diagram, you can easily see where uh, pressure 3 is equivalent to pressure 2, and volume 1 is equivalent to volume 4. And you can easily see where heat addition occurs and heat rejection occurs. So Q in and Q out. So same thing for the TS diagram. Okay, so S, so constant entropy, so that is where your vertical line is. And then constant pressure, so 3 to 4. S, constant entropy, isentropic. And then constant volume. So you will be required, of course, in your exam to draw the diagram. So again, so that it will be easy for you to memorize, have that code in your mind. So SPSV. Okay, so SPSV. I don't know why in this presentation, constant volume heat addition, but then this is in the diesel cycle. Okay, so this should be constant pressure, okay, as far as the diesel cycle is concerned. Okay, so process 2 to 3. So again, the difference, okay, so the difference between gasoline and diesel engine, spark plugs for gasoline, fuel injectors for diesel, air fuel mixture for the gasoline, so that's the intake stroke, air only, so air only for the intake stroke for the diesel engine. For the power stroke, it occurs at constant volume for the gasoline engine. For the diesel engine, it occurs in the uh, constant pressure process. So we now have this formula. Please take note of this one. So cut-off ratio. Okay, so volume 3 over volume 2, or specific volume. Okay, so if it is expressed per unit mass, so specific volume 3, specific volume 2, cut-off ratio. And then for the diesel cycle, thermal efficiency of the diesel cycle in terms of R and R sub C. So R sub C is cut-off ratio. R is compression ratio. K is 1.4. Okay, so K is 1.4. So 1 minus this expression. So R sub C to the K minus 1, and then K multiplied by R sub C minus 1. Then everything is multiplied in this expression 1 over R to the K minus 1. So same definition for the thermal efficiency. That is 1 minus Q out over Q in. So take note that we now have the term K over here, and somewhere CP and CV are cancelled. So I will no longer show you the derivation. So these are the things that you have to remember. In your exam, I think the formula is already posted. So I think this formula are already posted. So these are the relationships, the equations that we will be utilizing for the diesel cycle. So take note on the heat transfer, Cp and then Cv. So heat, constant heat, constant pressure heat addition. So specific heat at constant pressure. And then over here, specific heat at constant volume. So actually, you have less thing to memorize if you understand the diagram. So where does heat energy occurs? So for example, uh, heat energy occurs at constant pressure process. So where is it? So if it is constant pressure, then I know that the formula that I should use is this one. So what temperature? Delta T. So I base it from the diagram. Okay. So same thing over here. So let's have a sample problem. Let's have a sample problem here. So we have this ideal diesel cycle. So you are given the compression ratio of 20 and then a cut-off ratio of 1.3. So compression ratio, that is R. Okay, so that is R. Then cut-off ratio, so that is R sub C, 1.3. So we are asked to determine the maximum temperature of the air and the rate of heat addition to this cycle when it produces 250 kilowatts of power. So the state of air at the beginning of the compression is 90 kilopascal and 17 degrees C. So we are given the constants like R, then C sub P and C sub V. So I have this table. This table is very useful. So this table is very useful. Uh, so this table is very useful. Okay. So we again for the diesel, our code is SPSV, isentropic compression. So 1 to 2 compression, constant pressure heat addition. So 2 to 3, isentropic expansion 3 to 4, then constant volume heat rejection 4 to 1. So in this table, you can easily track your answer, and somehow it makes it easier to look at where you are solving. So for example, we are given pressure 1, then temperature 1, and then given also the other values. So let's have it here. Okay, so you are given 90 kilo Pascal. So let me, so pressure 1, this is 90 kilo Pascal. And then temperature is given as how much? 17. Okay, so 17. So temperature 1 is 17 plus 273. So right away, convert it into Kelvin. Okay, so right away, convert it into Kelvin. So how much is this in Kelvin? That is how much? 2
290, sir.
290. Okay, thank you. So 290 Kelvin. Yes, uh, let's disregard the decimal numbers, point 15. And then we are asked the maximum temperature. Okay, so maximum temperature. So if I were to draw the TS and PV diagram, so let's have the, so this is, okay, okay, so this is 1, and then 2, 3, 4. Okay, so, okay, so PV. So the highest pressure occurs between at this point, so 2 and 3. For the TS diagram, isentropic. So TS. So constant entropy S. So this is your vertical line, 1 to 2, then 2 to 3, 3 to 4, and then 4 to 1. So where does the highest temperature occurs from the diagram? So we can see that it's over here at point 3. Okay, at this state. So state 3. It is where the highest temperature occurs. So highest pressure occurs from the PV diagram is from here, 2 and 3. So pressure 2 is equivalent to pressure 3. So this is horizontal. This horizontal line. Then vertical line, vertical line. So this is at state 3. So meaning the high, what is being asked is temperature 3. Okay? So temperature 2 is expressed like this, T sub 1 times R to the K minus 1. And temperature 3 is simply temperature 2 multiplied by R sub C. Cut-off ratio, R sub C. Substituting temperature 2 for this one, then we now express temperature 3 in terms of R and R sub C multiplied by temperature 1. So temperature 3, so this is a direct substitution. So you are given 290. Then R, so compression ratio, we are given as 20. So let's go back with the, so compression ratio. So this is R, 20. And the R is volume 1 over volume 2. So where is R? So already here. Okay, so R is volume 1 over volume 2, or specific volume 1 over specific volume 2. So that's why in this one, I have volume expressed in cubic meter or specific volume. So when this expression, when this equation is divided by mass, so volume per unit mass, that is specific volume. So solving for specific volume is like this. So RT over P. So if volume is given, then you use this one. So this one becomes volume 1 over volume 2. I hope I am clear with that one. So no confusion. So compression ratio, this is given 20. Then R sub C. So R sub C is also given as 1.3. So R sub C, where is it? Okay, so cut off ratio. So cut off ratio, 1.3. Okay. So following this one, uh, we now get the answer for the highest temperature in the cycle, and that is temperature 3. Okay, so then, uh, knowing what is thermal efficiency, okay, so what is thermal efficiency? The formula is work net over Q in. So what is asked is the maximum temperature, then rate of addition heat addition, so Q in, when it produces 250 kilowatts of power. So okay, so work net, so that will be your 250, so that is the power produced. Okay. And then thermal efficiency is expressed in terms of R and R sub C. So these are direct substitution. And finally, you get the value for Q in. Okay, Q in. So I hope we are clear with this. So it's a bit shortcut. So if I were to do it, I'll solve first for thermal efficiency. So I'll solve for thermal efficiency. So 1 minus 1 over R, okay, minus 1, and then okay, so on and so forth. Then after I have this number, so I now have this number, so whatever the answer is, and then I'll go with that expression wherein you have your Q in. So Q in is also expressed as let me go back with the instead. Okay, so over here. Okay, so thermal efficiency is expressed like this in terms of R and R sub C. Okay, and then going back with this original equation, the thermal efficiency is work net over Q in. So work net is given as 250. I already solved this using this one, so I will now solve for Q in. Okay, so that is how if I'll be doing it. So anyways, it's just the same. It's just the same. Okay, so we now have this another sample problem. So we have an ideal diesel engine that has a compression ratio of 20. So again, compression ratio, that will be your R. Okay, so small r. Okay, so small r. Let's not be confused with the uppercase R, wherein it is the gas constant. So compression ratio. And that's why I prefer to use R sub K. But in the book, it's only R. And then uses air as your working fluid. So state of air at the beginning of compression. So this will be your pressure 1 and then temperature 1. If the maximum temperature of air is not to exceed 2200 K, 2200 Kelvin. So maximum temperature, where does it occur? At state 3. Okay, so at state 3. So we are to determine the thermal efficiency and then the mean effective pressure. And with this, I would like to leave this as a sample problem for you. So how to solve this one? So it's already here in the table, the values that you'll be needing. Okay. So what is the thermal efficiency? So again, thermal efficiency is expressed like this. Okay, expressed like this, thermal efficiency. Please take note of this one. And then what else? Mean effective pressure. Okay, so mean effective pressure So where will you get the mean effective pressure? Over here. Work net over volume displacement. So volume displacement is simply from the so volume displacement. So if this is volume, so take note. Oh, wrong pen. Okay, so this is volume. So PV diagram. So this is okay, and then over here. So that will be this volume minus this volume. Okay. So this is your displaced volume. This one. Okay, so this one. This is your displaced volume. This is your displaced volume. So volume one minus volume two. So first three correct answers will be awarded with additional points. Anyone who already has an answer? Okay, so not yet. Okay. So try to solve for this one. Okay, so the answers are already posted, but try to solve it on your own. Try to solve it on your own. Okay, so as a hint, as you can see, um, mass is not given. So instead of volume, we are using specific volume. Okay. So you solve for a specific volume. So volume per unit mass. And then solving for volume uh, for specific volume. So you should be able to get R sub C. So once you get the value for R sub C, so you are now ready to solve for letter A, thermal efficiency. So thermal efficiency in terms of compression ratio and cut-off ratio. Let me show you again the formula. Okay. Okay. So in terms of R and R sub C for the thermal efficiency. That is R sub C 1 minus 1 over R to the K minus 1, and then this one R sub C to the K. So take note, this one R to the K minus 1 is different from here. So R sub C to the K and then minus 1. So this is different. K minus 1 in this part, this is the exponent K minus 1. This is the exponent K minus 1. So this one is the exponent for this expression is only K, just to be clear. So R sub C to the K minus 1. Compared with this one on the denominator, R to the K minus 1. So just to be clear. So as I've said, how to get R? So you need to use the volumetric ratios. So R is given, but R sub C is not given. So you need to solve for volume 2 and volume 3, or specific volume. Okay? In this case, specific volume. So solving for R sub C, then you should be able to get the thermal efficiency. And for the thermal efficiency, once it is solved, then you now you can now solve for worknet. And solving for worknet will now lead you to be able to answer the second question for the mean effective pressure.
A few moments later.
Anyone who already has an answer? Not yet? No answer? Okay, so A is 0.635. That is the thermal efficiency. The thermal efficiency is 63.5%. Let's see. How about the other? So let's see. Any other answer? Okay, so 63%. Uh, okay, okay. So 6%. So let's see. Okay, so let's see if the answer is correct. All right, very good. So it's 63.5. Okay, very good. Someone answered the it's correct. Let's see. So 935. Who's the kilopascal? Ah, okay. So you made a mistake, unfortunately. So the answer is 935.21. So in this solution, um, he used the formula in terms of temperature for worknet. Okay, so worknet is simply QH minus QL. So QH minus QL. So you have this one. So he solved for the temperatures. Then CP and CV, so specific heat at constant pressure and constant volume. So that is given 1.005 and 0.0718. So that's it for today. I will see you on our next session. And don't forget to like and subscribe. Yeah, all right.
What's up? Slap us. Slap like now. Slap the like button now. Don't worry, I'm not forcing you.